Hi, this is Dane Quinn from the University of Akron, and today we'll do an example with planar dynamics. So here's the problem. We have a block of mass m that is in contact with a rough surface, and the coefficient of friction between these supports and the ground is mu. Now it's pulled by a horizontal force with magnitude F that is greater than 0, so here this is a force to the right, and it's applied at a height of d above the ground. So the mass center of the block is located at a height of h and is centered between the two supports. And I'd like to find the maximum value of the force, so this value of the force F, so that the block does not tip when it's released from rest. So again, the idea is we have this block and it's sitting here and we apply a force, and I want to know what happens, right? Does the block slide along? Does the block tip over as it slides? Does it just stay there? Does it stick? Or the other possibility is that it immediately begins to tip as it rotates on this front support. So following along with the solution methodology that we apply for these problems, we'd like to first identify the forces that act on the block. Right, so these forces arise from a number of places. So there are forces that arise from the normal loads at the supports. So these will be, say, a force here, and we'll say this is N1, and a force here, N2. So again, these normal forces are N1 and N2. Then certainly there are forces due to friction that exist at both of the supports. So we'll say that this force is friction F2, and here we have friction 1. So again, we have FR1 and FR2. We also have the weight of the block, so the force due to gravity, and we will describe that as W. And finally, we have the applied force, F, as seen in the problem statement. So here, that is a force F in the I direction. Now notice that at this point, I am just trying to identify that these forces exist. I am not necessarily saying what they are, or really much about them at all, except just trying to identify that they're there. So the distinguishing feature about this problem, and in particular how do we tell when the block rests on the surface versus when it tips, is related to these normal forces. So if the block rests on the surface, then the normal loads have to be in the plus j direction. Because if the normal forces were in the minus j direction, again here j is sort of up. If the forces were in the minus j direction, that would imply that the surface was pulling the block down. So the forces would in some way be adhesive. Instead, as long as the block is resting on the surface and not tipping, these forces are directed up. So here's what we're going to do. We're going to assume that the block does not rotate. So when we solve for momentum balance, we're going to make the assumption that the angular acceleration of the block is 0. and then find the maximum value of the applied load, so we'll call that F max, so that either of these normal loads in 1 or in 2 is adhesive. And again, that implies that the force is in the minus j direction. So it would be pulling down on the block. So that's kind of our solution strategy, right? We're going to again assume that there's no rotation. So the angular acceleration of the block is 0. And then we're going to look for the value of the force that makes one of these two things adhesive. So again, in the minus j direction. Alright, so to start off with, we will initially define coordinates and directions. Well, the directions were actually given to us as I and j in the problem statement. But I'll go ahead and redraw those. And then for coordinates, remember what coordinates are. They are measurable quantities that help us define the configuration of the system. Right? So it's something that we can measure that will tell us where the block is at. Well, obviously there are a number of choices, but the way that I will choose to measure the block is in terms of the horizontal displacement, right, from some reference point. And I'll call that x. So we will measure the displacement of the block as x, again from some reference point that we choose. So now, since the block does not rotate, we don't need to measure its rotation. So there's no angle that we need to describe in terms of the rotation of this block. And that again implies that the angular acceleration of the block is 0. And with this coordinate x, we find that the acceleration of the mass center of the block, so let's let g be the mass center, is x double dot in the I direction. So again, I is a measurement, and it's related to the acceleration as x double dot in the I direction. So these are the kinematics. Again, we've assumed no rotation. We found a way to measure the acceleration of the mass center. So now we'll turn to the free body diagram. So really, we need to go and identify what these forces are in terms of coordinates and directions as necessary. So we have the applied load here. Recall that we had the weight. Right, so the weight will be minus mg in the j direction. The normal loads will be assumed to be n1 in the j direction and n2 in the j direction. And then we have friction forces. So I will describe both of those as Fr2 in the I direction and Fr1 in the I direction. And so you may look at this and go, well, wait a minute, the friction force should be to the left, right? Because the block should be sliding to the right. And I would probably agree with you. But the way that I will introduce that is through the relationship between the friction force and the normal load. So in particular, we define the friction force so either one of these, Fr1 or Fr2, is minus mu times n, where again n is the appropriate normal load, times the sine of x dot. So this is where the direction of the friction force is introduced. If x dot is positive, so the block is moving to the right, then the friction force is negative. So it again is in the minus I direction. However, if the motion of the block was to the left, so that x dot was negative, then the sign of x dot is -1, and then that combines with this, and the friction force is positive, so that it is to the right. So this is the value whenever x dot is greater than 0, so when there is motion. In contrast, if the block is not moving, then the value of the friction force is whatever is required to maintain equilibrium. So again, this F stick is the force required to maintain equilibrium, or in particular a state of stick. And we have our inequality that the magnitude of the friction force must be less than or equal to mu n. So this would tell us when we transition between a state of stick and a state of slip. So these are the forces that act on the system. And again, we have a description of the friction force. We have the kinematics, so the angular and linear acceleration of the block. And now we are ready to apply the equations of motion. So we have linear and angular momentum balance. Linear momentum balance, in particular, sum of the forces, is mass times the acceleration of the mass center. And for this system, again, looking back, we'll just take all of these forces and sum them up. But we have to make sure that we include the directions, because directions are important. So that becomes, in the I direction, we have the applied load, we have the two friction forces, in the J direction, we have the weight, minus mg, and we have the two normal loads, N1 plus N2, and that is the mass of the block times the acceleration, which was x double dot, in the I direction. Then we also have angular momentum balance, so we'll take some of the moments about the mass center, and we'll set that equal to the moment of inertia of the block times the angular acceleration. But of course, here we're assuming no rotation, so alpha is equal to 0. Now, going and calculating the moments produced by these forces, let's go back and look at this. So again, we're taking moments about the mass center, g, from each of these forces. So the weight produces no moment because it acts through the mass center, but moments are produced by the remainder of these forces. Now the applied load was at a height of d. You can actually go back and look at the problem statement here. The width of the block was w, and the height of the mass center was h. So as a result, we can find that the total net moment acting on the block is minus F times d minus h plus the friction force at the left support times h plus friction force at the right support times h minus N1 times w over 2, that was the width between the supports, plus N2 w over 2, and all of those are in the k direction. And again, because there's no angular acceleration, this has to vanish. Now, I just wrote this down, but you might want to go back, look at the original problem statement, look at the free body diagram that we developed, and come up with this expression for the net moment acting on the block on your own. But so again, these are the equations of motion, and we have three scalar equations. Here we have components in the I and the j direction. Here we just have components in the k direction. So taking components in, well, for these two equations, we see that in the I direction, F, the applied load, and the two friction forces equals mx double dot. Then, in the J direction, we have minus mg plus n1 plus n2 equals 0, because of course there's no J component in the acceleration, so we effectively have 0 in the J direction here. Finally, we have the angular momentum balance equation in the K direction. Right, so that's going to look like minus F d minus h plus Fr, friction force on the left support. And these are the moments produced by the friction forces. Then we have the moments produced by the two normal loads, minus n1 w over 2 and n2 w over 2 equals 0. So we have these three equations, and then in addition we have our friction law from our previous discussion from the free body diagram. So each one of these friction forces is related to either the normal load or the motion in this way. So now if I look, how many equations do I have? I have 1, 2, 3 here, and then I have two more, right? An additional equation for each friction force. So really I have 5 equations. And how many unknowns? Well, I've got the two friction forces, that's 1 and 2. I have the normal loads, n1 and n2, so that's unknown number 3, unknown number 4. And then finally I have the acceleration of the block, so that's 5 unknowns. Again, I have 5 equations, 5 unknowns. I should be able to come up with a prediction for the motion. Now, friction has two cases. One of them is stick and one of them is slip. So we must consider these two cases separately. Or we must consider these two states of motion. So in the case where the block sticks, there's no motion, and x double dot is equal to 0, with the constraint that each friction force is less than or equal to mu times the corresponding normal load, or we have slip. So when the block slips, the magnitude of x dot is greater than 0. So we don't know the kinematics, but we do know the forces. In particular, the magnitude of each friction force is equal to mu times n. So these two cases are different. In stick, we know the kinematics, right? So we know x double dot, but we don't know the forces. They have to be less than mu n, granted, but we don't know what they are. We have to solve for those. In cases of slip, we don't know the motion. I don't know what x double dot is, but I do know what the friction forces are. They are equal to mu n, and of course they oppose the direction of the motion. So we know one of these two things, either the kinematics or the forces, but we don't know both. So now let's look at these two cases of motion, and we'll consider stick first. So when the block sticks, x dot is identically equal to 0. It's not just equal to 0 at an instant in time, but it's always equal to 0. So as a result, x double dot is also equal to 0. And the equations of motion reduce to the following. F, so we had linear momentum balance in the I direction. So that's F plus Fr1 plus Fr2 equals 0. And I'm going to highlight the unknowns in blue here, and the known quantities will be left in black. So then we have N1 plus N2 minus mg is equal to 0. So that was linear momentum balance in the j direction. Then angular momentum balance is minus f times d minus h plus fr1 times h plus fr2 times h minus n1 times w over 2 plus n2 times w over 2 equals 0. So now one of the unknowns, again, was given to us by our kinematic state, namely friction, so x double dot is equal to 0. Then we have three equations for, unfortunately, 4 unknowns. 1, 2, 3, 4. However, if you notice, these friction terms always appear together. Right? So I have fr1 and fr2, and down here I can factor an h out of these two terms and find fr1 plus fr2. So even though we can't solve for all 4 of the unknowns uniquely, we can solve for n1, n2, and then the total frictional force, which is fr1 plus fr2. This is actually an indeterminate problem, but again, we can solve for the sum of these two things. So in looking at that, we see that fr1 plus fr2 equals minus f. So this is the net frictional force, and it has to balance out the applied load. Again, there's no motion, right? So the forces have to balance. And really what we're saying here is that the friction force, the total friction force, balances out the applied load, which really totally makes sense. So then if I look at these other two equations, right, I have n1 plus n2 equals mg. So now this last term from angular momentum balance can be reduced to the following. And as I do this, I'm going to go ahead and substitute in that the net friction force is equal to minus f. Right? So I'll actually factor out a minus f from these two terms. And I'll factor out the w over 2 from these last two terms. And so we end up with minus f times d minus h, right, from this first term. And then we had a minus f from the friction forces, right? So we have plus h, and then minus n1 minus n2 times w over 2 equals 0. So a couple of nice things happen, right? In particular, these h's cancel out. And so then I can solve for n1 and n2. So when I do that, I have n1 equals mg over 2 minus f times d divided by w. And I have n2 equals mg over 2 plus f times d divided by w. Moreover, we still have our inequality from the friction forces, right? And that inequality, so for each individual friction force, was that the absolute value of the friction force was less than or equal to mu n. So now I will use this together with my expression for the friction force to show that F is equal to the absolute value of Fr1 plus Fr2, which has to be less than or equal to mu times N1 plus N2. So now, if I add these two expressions for the normal loads together, this is simply mu mg. So from this, we see that the applied load, F, has to be less than or equal to mu mg, in order for stick to occur. Not only that, both N1 and N2 have to be positive. So because that was our condition for not tipping, right? If N1 or N2 are negative, then that implies an adhesive force, which is not possible, so that the block tips. So if I go back and I look, as long as F is positive, N2 is going to be positive, because I have mg over 2 plus Fd over W. Actually, let's go back and look at the free body diagram. So what that says is that this front load, N2, is always positive. Right? There's no way the front can come off of the surface, provided the block is stuck and not moving. However, N1, let's go back and look at that, N1 is mg over 2 minus F times D divided by W. So it is certainly possible that this could become negative if F is large enough. So at the critical value for which the block begins to tip, let's identify that force as F star. So at F equals F star, so this is a specific value of the force. Let's look for the case where N1 is equal to 0. And at that force value, the block begins to tip. So N1, remember, was mg over 2 minus, and now we're looking for this specific value, F star times D divided by W. This N1 is equal to 0. This is our tipping condition. And so we can solve this. F star equals mgw divided by 2d. So this is the critical load at which the block begins to tip, provided F is less than or equal to mu mg as well. Right? So this was for sticking, this is for tipping. So now let's look at what happens when the block slips. So if we have slip, then F is greater than mu mg, right? Because if it's less than that value, the block sticks, right? So again, F has to be greater than some certain threshold for the block to move. So this implies that x double dot is positive. And as a result, we can use our friction law and say that Fr1 is equal to minus mu N1. And here we're making the assumption that the block moves to the right because it was released from rest. X double dot is positive, and so again then x dot begins to increase and is positive as well. So the friction force acting on the left is minus mu N1, while Fr2 is minus mu N2. So with this, we can write our equations of motion, and we had three, two from linear momentum balance, one from angular momentum balance, as F minus, and I'll go ahead and I'll substitute in these values of the friction force. So it's mu, and again, as I did before, I'm going to write the unknowns in blue. So mu N1 plus N2. And so again, I will write the unknowns in blue equals m times x double dot. We also have N1 plus N2 equals mg. And then finally, angular momentum balance minus F d minus h minus mu N1 plus N2 times h minus N1 minus N2 times W over 2 equals 0. So I can solve for these unknowns. And I'm going to go ahead and write that down. It's just some algebra. You can pause the video here if you need to and solve for N1 and N2 and x double dot based on these three equations. But what you find is that x double dot is equal to F minus mu mg, and N1 is equal to mg over 2 minus, now we have the following expression, F times d minus h plus mu mgh divided by W. Again, this is all just algebra. And so I would urge you to pause the video solution at this point and work this out. But at this point, I trust that you can solve three equations with three unknowns. mgh divided by W. So this is the acceleration. This is the normal load on the front. This is the normal load on the back. Or, I'm sorry. And so this is the acceleration of the block, x double dot. This is the normal load on the left support, the back. And this is the normal load on the front support. So now, as before, both of these two things have to be positive, N1 and N2, for steady sliding. It's a little more complicated in this case than it was for stick, because either one of these two things could possibly vanish depending on the sign of d minus h. So, in particular, if d minus h is positive, and actually let's go back and look and see what that was. So d minus h looks like the height between the applied load F and the center of mass g. So really d minus h is the height above the mass center for the point of application of the external force. Right? But again, if that value is positive, then this is always positive, this last piece, but then because it subtracts off of mg over 2, N1 could be negative. In contrast, N2 is always positive if d minus h is positive, because then both of these terms are positive. So let's look at those two cases separately. Right. So once again, both N1 and N2 must be positive. So now, two cases. First, let's consider d minus h, again, the height above the mass center of the application of the force. Let's look at that as positive. Right, so once again we have stick or slip. So if F is less than mu mg, less than or equal, then we have stick. So here, we're going to plot the behavior of the system in either stick or slip or what we'll call rock or roll as a function of W over 2. Right, so that's the width of the block, well, half the width of the block, and this sort of non-dimensional force, which is the applied force F divided by the weight. So for this case, this critical value is F over mg is less than mu. So that would be down here, right? So again, f over mg is less than mu. So what happens in this region down here? Well, we have the possibility of stick, or we have the possibility of roll. So roll I'm defining as the block being stuck and then just rolling over. And remember that the critical condition for that was given as f star mg w over 2 divided by d. So looking at that, we can find that f star over mg equals w over 2 divided by d. So if f is less than this value, or in particular if f over mg is less than this value, which again is w over 2 divided by d, then we have stick. And if it's greater than this value, then we have roll. So what does that look like? Well, that is going to produce a line like so. So this is the value of f star over mg that separates stick from roll. And again, so we have to be less than this value, and we have to be less than mu. So really what that implies is in this region, here, we have stick. While in this region, we have roll. So, if w over 2 is large enough, which means that the block is very wide, then the block is expected to stick. However, if w over 2 is small enough, and the force is large enough, we expect the block to roll. Now, if the force becomes too large, the block slips. So then we have to go and look at our slip analysis. So this would have been f greater than mu mg, or f over mg greater than mu. So now, we had said that N2 was always going to be positive. But N1 equals 0 at some critical level of force. And again, we'll call that F star. And that critical value is given by our equation for the normal load. N1 equals mg over 2 minus F star d minus h plus mu mgh over w equals 0. Or, solving this equation for F star, we find that F star, and we can actually solve for F star over mg, is equal to 1 divided by d minus h, there's that quantity again, times w over 2 minus mu times h. So now, if I look and I plot this function as this value of f star over mg as a function of w over 2, again it's a straight line, but it doesn't pass through the origin because of this mu over 2. Instead, it actually connects up with this line, right? But it goes off at a different slope. And you could actually extend this back to figure out what this value is. And this value actually is mu times h, while the actual value of this transition point occurs at w over 2 equals mu times d. So now we see that in this region, again, w over 2 is large enough relative to f over mg, then the block slips. While if w over 2 is small, but f over mg is large in this region, we would say that, I'm going to say that the block rocks. Right? So this is sort of slipping and tipping. And it's going to rock in the positive direction. Right? So here, if it rocks that way, I will denote positive. While if somehow, and we'll see this in the next case, it rocked that way, it would be, we'll say rock negative. And this is rock positive. Okay, so we've done the case where d minus h was positive, but what happens if the force is applied below the mass center of the block? That's actually a little more complicated because now either N1 or N2 could vanish. So recall what those look like. Right? So here N1 is mg over 2 plus f h minus d minus mu mg h divided by w, and N2 was mg over 2 minus f h minus d minus mu mg h. So I'm just rewriting these so we can refer to them in a second. And again, we have two cases, slip versus stick. So stick occurs for f less than or equal to mu mg. So in this case, again, we have the same results as before. Namely, the block tips at f equals f star. F below that, it sticks. F above that, again, it tips. So this value of f star, in particular f star over mg, was given as w over 2 divided by d. And those are exactly the same results as we got before. Here, f over mg has to be less than mu for this case of stick. And then, once again, we have two cases. This is the line f star over mg. And, as before, this point corresponds to mu times d. And this line distinguishes stick from roll. Those are the two cases that happened when the block was not sliding. It can either stay there or it can just roll over on the front edge. Now, if f is greater than mu mg, either N1 or N2 can vanish. For some value of f star. Right. And there's a different value for each of these two cases. So now, looking back into this expression, we'll set N1 equal to 0 with f equals to f star, and we solve for f star. In particular, f star over mg is equal to 1 over, and I'll write this as h minus d, now, because we're looking at the case of d minus h less than 0. So h minus d is going to be positive. And then mu times h minus w over 2. While if n2 equals 0, we can solve for f star as 1 over h minus d mu h plus w over 2. So these are the two values of the force that transition between slip, just steady slip, and rocking. Let's look at this case first. This is the corresponding case to what we had last time, where n1 vanishes and we rock in the sort of positive way. Now if I draw that line, so again, f over mg has to be greater than mu, and this line looks like the following. I can actually extend this down and see that it would intersect f equals 0 at 2 mu h. But so this region here above the slipping line, but below this, we will refer to as rock plus. Then if I go and plot this expression, I have a line that sort of comes here, and it would extend all the way up and continue on sort of forever. So now we have the three regions. Steady slip is over here. Rock in the minus direction, so that would sort of be reverse rocking, is in this region. Rocking in the positive direction is here, and recall we define those positive and negative directions in that way. And then in this region we have roll, so that's defined as the block not slipping but just tipping over, stick, and again slip. So this is a pretty exhaustive analysis of this problem, and I've tried to go through and give you an idea of sort of what is possible, because this is really what dynamics is about. Dynamics is not just about, you know, coming up with equations and calculating numbers. Dynamics is predicting what's going to happen. So it's nice if you can develop this sort of understanding about what is going to happen as the different system parameters change, right? So in particular for this problem, right, let's kind of look at what we might have had for the block. So I had the block here, I had the mass center there, and I'm pulling on sort of the lower half in this case. And we see lots of interesting things could happen, right? If the force is low relative to the coefficient of friction, we have the possibility to stick, right? So nothing happens. We have the possibility to roll, right? So this block would just kind of roll over on this front corner point. But if the force is large enough, right, or equivalently the coefficient of friction is small enough, then the block could undergo steady slipping, right? It could rock in the sort of positive direction. So as I pull, right, it might just sort of slide and tip over. Or it could actually tip backwards, right? So this would be kind of like pulling the feet out from underneath the block. So that would be a large applied force, and then the block would sort of slide to the right, but then undergo what we've defined as rocking in a sort of a negative way. Again, this is dynamics. It's about understanding the response of the system and characterizing what happens as the parameters change. So thank you very much, and we will see you later for more examples. Goodbye.